जूम पे नहीं और लाइट एक्स्ट्रा नहीं फिर से रिवर्स करें actually hide when click on click on more and say page. Yeah, you might have to click on the slide. Yeah, now I have to. With that? Yeah.
So happy to have Anand give a talk today. Anand completed his PhD in 2021, right? Yeah. I think this was the tutorial that Anand and Karthik were going to present in WSC, but then you were not allowed to travel.
I was not allowed to travel.
And he kind of was not well, so it didn't happen.
It happened. So we are the second choice.
So we can have be the first ones here instead.
Yeah, so you'll be the first ones here. Yeah, but we were the second choice.
But he wanted to prepare.
Yeah. So thanks for the invitation, Sandeep. Thank you everybody for attending towards evening. It's a pleasure to be back. Usually I'm sitting on that side, so it's a little unfamiliar amazing here. So most of this is joined up with Karthik. About 80% of it. The last part I'm going to show you is joined up with Anirudh, who's in Penn State, and Rakshit, who's like a really bright undergraduate student in CS. So someone to look out for. And the basis of the talk is like making safe. And over the last couple of years, unfortunately, we have seen what happens when extreme events affect various operations. So whether it be the energy crisis a couple of years back, whether it be COVID-19, whether it be this ship getting stuck in the sea, these extreme events, although they occur infrequently, they will lead to massive loss of revenue, to loss of life, and they generally to large-scale disasters. And as a policymaker and as an operations researcher, it is imperative that in our decision-making processes, we incorporate the presence of such events, and our decisions sort of guard against the occurrence of these events while keeping while being good on normal days. Okay, and when all of this is just context. What I'm going to do, I'm going to show you like a mathematical formulation for this. So the motivation behind the talk is just making decisions in presence of rare events. And the mathematical formulation is as follows. I specialize this to one particular case, but nothing prevents us from extending whatever I'm going to say to the more general setting shown on this slide. So the formulation is as follows. So rho here is a risk measure. Okay, and it depends on an underlying distribution P star. P star you do not know, but you have access to samples. Okay, so it's an unknown distribution from which you can sample. Okay, well, not unknown, I'm going to assume that is no P star low density, but you can't evaluate this in flow form. That's what I mean by it. Okay, so you have access to samples of P star, and theta is your policy. So what decision you are going to make? So rho is going to be a function of a decision theta and underlying distribution P star. And I'm going to assume that it has nice optimization properties and that is convection. So it's a convection. This say capital theta is a service constraint. So, like I said, on more average days, whatever decision your policy you make must perform well. So, what you want to do is you want to minimize the tail risk. You want to minimize the tail risk such that on average days you do well. What do I mean by expression when it depends on what's or the most risky beta factor about. So, in order to show you the picture, here are the samples of data which are given to you. Rho is only evaluated on the extreme right samples, so which I showed you. So it's evaluated only on the worst beta factor. Typically, beta is going to be between 10 power minus 2 and 10 power minus 4. So it's going to be a small number. Okay, so this is evaluated on a rare event. So this is rho is the measure which is evaluated on the distribution page. So it kind of captures the events. Okay. And I'm going to sort of, okay, so this is a more general setup, but I'm going to do some kind of specialized to one particular risk measure, and that is conditional value-at-risk. So, by the way, since this is a tutorial talk, please, if you have questions, please feel free to ask. Okay, so I'm going to specialize to one particular risk measure, there is conditional value at risk. So for a loss L, so think of a loss as being a portfolio in which you invest, so how much you lose on the portfolio. For a loss L of a random of a stochastic outcome X and a decision theta, the conditional value at risk at a level 1 minus beta is simply the average of the loss over the largest beta fraction of outcomes. Okay, so it's only evaluated over the largest beta fraction of outcomes, so it will take this beta. And what this optimization formulation is doing, it is minimizing the conditional value at risk subject to certain conditions constraints. Now, a concrete example which I want you to keep in mind is portfolio optimization, where you are investing in a portfolio. So you're minimizing the conditional value at risk of the portfolio at some 1 in 100 level.
So X is the returns from
X is the amount, yeah, it's the that.
Theta is the amount we invest.
Theta is the amount, yeah.
And you want to look at the losses from
Yeah.
when we the bottom 1%.
Yeah, so the bottom cost and on the average, you want to make you want to make a target.
So it's a one shot.
It's a one shot product, yes. It's a one shot product. So
It's not like online.
no. So whatever you show, right now is one shot. So you're just given the data. You want to sort of get the portfolio which is based on the deal.
So the data is available offline.
Yes, data available online. This is offline. This is entirely.
Okay.
There are online variants, but whatever. I mean, so as I show you, whatever we have is kind of security. So there are online variants. Okay, so this is one version. Another version is very related. So what you do is sort of build risk versus return using this parameter lambda, this called risk capital. So this captures how much you assign to the need, this captures how much you assign to the tail. Depending on lambda, you get a risk return trade-off and you optimize this. So these two are similar. A third one which I will show you right at the end of the talk is something called as chance constraint optimization. So this is more towards safety. So what this is saying, if you want to maximize utility, so use some utility function of a policy. You want to maximize utility such that the the P bar of some loss is controlled to some safety level. Okay, so the smaller the beta, the more the safety which you want to incorporate into your problem. So this is a utility maximization problem. This is a risk minimization problem. They are kind of used of each other, and whatever I'm going to show you is going to be applicable to both. So I will focus mainly on this. Towards the end, I'll do some numerical results on this. So this is important. Okay. Generally, like whenever these constraints occur in the whenever these rare expectations occur in the constraint, this is much harder to solve. So this is more of a numerical explanation right now, which I'll show you later. Okay. So is this okay? So any questions on this? Okay. So good. So this is the problem which we are actually going to focus on.
This whole function is convex, isn't it?
Okay, so if the loss is convex, then it will be convex. But whatever results I'm going to show you don't really require it to be convex. If you want to get a Taylor theorem, then the convexity comes. But variance reduction, what I'm going to show does not require convex.
So what are your performance measures? So you have only access to the data, right? You don't have.
Yeah. So this what we have to do, you have to replace this with this empirical average, and you're going to compare that empirical average with something called an importance sampling. And how much is the error, variance error in that estimation is what we are going to use as the comparison. And then empirically we use regret. So like what is the outer sample performance? That's what we use. Okay, so great. So this formulation by itself has a lot of applications. I just showed you this one, portfolio optimization. Recently people have started, I mean not very recently, but people have been using CVAR as a sort of a proxy for power network failure, and there has been a lot of literature since about 8 years ago. Supply and pricing risk, I mean, naturally, I mean, when you are trying to minimize delays while routing another package, it sort of CVAR shows up naturally. So this is a nice paper by Jose Nurture and his authors of this. Most interestingly, CVAR has also produced way to machine learning in fairness, because when you're training an algorithm to be fair to a minority population, you can always treat it like as a CVAR minimization problem, where the worst beta fraction of outcomes basically becomes a minority, and if your algorithm is doing kind of well on that beta fraction of outcomes, then the algorithm is fair. So this paper of Williams is very nice if you would like to consult.
So how sensitive is to the value of beta? I mean, like,
so there is an asymptotic that we have, and it shows that under reasonable condition this is not sensitive much. So it will basically just the decision will be invariant as you make the problem rarer and rarer. I won't show it in this, but we have a separate result. But it basically the decision will just remain constant. upwards scaling. Okay, so as beta goes to beta. Alright, so I mean, this is a very, very well motivated problem. It has a lot of applications.
Then you can also study this problem asymptotically, right? Just
You can
evaluate the expression.
Yeah, but I mean, those are not that whatever gets living in convex, and then the rates of convergence will be very poor. So although you will get an asymptotic, the rates of convergence will be very poor depending on how well we have done.
It becomes the starting point for the problem.
It becomes the starting point. One can do that. So in fact, like in the data-driven setting, which I don't present here, that is exactly what we do. So we analyze the derivative from this. Okay. So why this is very, very useful? Because this is the expectation, I just showed you a nice picture. Evaluating this can be statistically challenging. So like, because you can't actually get this objectively closed form, and doing an asymptotic is going to kind of lead to a bias which you cannot quantify. So like statistically, the error in evaluating tail expectation is very large. And let me just show you one. And to motivate this, let me just go back to this is something which you will be more familiar with. So here's the problem which is minimizing a conventional expectation. Okay. So you're just finding the decision which gives a minimum risk, no tail. And we cannot evaluate this expectation. So what you do, you take your data and you replace it as that. Okay. And central limit theorem for this are well known, confidence intervals for this are well known, how the optimal decision varies, how the as behavior function everything is there. Okay. So this is doable. Now let's go to C bar. Remember what I told you? C bar is the average of the loss outcome over the worst beta factorial samples. So what you can do is you can just take these worst beta factorial samples and again the sample average. And now can someone tell me what goes on?
Rarity.
Yeah, but okay. What happens? So what goes on is that if you have 10,000 samples and your beta was 1,000, only 10 samples are going to minimally contribute to the average. And doing statistics with a 10 sample average is never good. So, so you cannot evaluate this objective empiric just using empirical averages. And there has been a lot of work, especially in portfolio optimization, which shows that even at rarity such as 1 in 10, you require 30,000 samples of data to make any meaningful difference. So that's a huge number. If the rarity goes to 1 in 100 times, it becomes 10 times, if it goes to 1,000, it will become 100 times. So you require enormous amounts of data. And in a lot of these applications, these are not big data applications, but other small data applications. So you typically have only 200 to maybe a few thousand samples. So sample analysis is just out of question. Okay. So what do you do? Well, we use something called an importance set. And here I'm going to assume, here is where I'm going to assume that the density of X is known to you, but you cannot actually evaluate this objective. Okay. So it turns out, a seminal result in Rockefeller and all 20 years back, that the C-bar minimization problem which I showed you, so minimizing this objective, can be just recast as a nice optimization problem, like this. Now I want you to think of U as a large number. So this expectation, the objective inside the expectation only gets turned on. So the plus is like a max comma 0. It only gets turned on when this class exceeds. So it's a rare event. So the rare event nice number. Okay. And why was the sample average being badly? Because your distribution is placing very little mass in the tail event, so you never saw enough. So we say, okay, instead of sampling, because we know what the density of X is, instead of sampling from this guy, let's sample from this guy. An alternate distribution which places more mass in the area of interest. Okay, let's sample from this. However, when you sample from an alternate distribution, you're not evaluating this objective, but a bias. So what we need to do is we need to kind of relay this in order to recover the unbiased objective. So assuming this is the distribution of X, what you do is you kind of sample from this guy, relay the objective by a likelihood function, which is just the ratio between the densities of X and Z, and then evaluate this objective. Now you can sample from Z, so you can replace this with an empirical average. And because this event is no longer rare under Z, if you should choose this distribution, alternate distribution properly, the curve rarity gets this product. Okay, and that's important sampling. So you basically sort of sample from an alternate distribution which places more mass in the rare event. Okay, and now you can just solve this optimization. So rather than solving this sample average version, you solve the weighted sample average. The weights being the likelihood which eliminate the bias associated with the alternate distribution. Okay, and the only sort of catch now is we choose what is a good alternate distribution to sample for. Once you do that, this is going to work well. So how's that? Well, there was a float to it. And this has been studied a lot in the rarity simulation literature, probability estimation. Typically, this is what you're going to do. You'll have a model. So by model I mean loss L and X, the distribution of X. What you'll do is you'll first propose a family of important sample distributions. Okay? And how you do this? You'll do something called a large analysis for the problem, for that particular problem. Depending on the large analysis, that is the risk effect. Now, family basically contains a large number of distributions characterized by a certain set of parameters. So, what you will do is to find what member of that family suits your problem the best, you will set up an optimization. Typically, revolving around the variance of your objective. You try and minimize the variance of the objective based on some, you choose something which minimizes the variance of the objective under the importance of. Once you set up the optimization problem, you will solve that optimization problem, and whatever member of that family solves that optimization problem, you will use as input. So once again, you will do a large analysis for that particular problem. So this is problem independent. You will set up an optimization problem, you will solve it, and you will get the importance. So this will be the traditional workflow. And this will work very well for probabilities. However, when a decision is involved, so the theta is involved, this does not work. And I'm going to show you why I list a couple of features. So here's a simple portfolio loss. So theta is how much you invest in a particular set of stocks, two stocks here. X is the loss due to stocks. And I show you two different portfolios. So the first one invests 0.2 in the first stock and 0.8 in the second. The second one is 0.8 in the first, 0.2 in the second. And remember what important sampling distribution was. It was placed mark where the variable is happening. And the variable is given by the rate loss. Okay, so I've actually generated conditional samples of Lx theta greater than equal to U. Okay, so the variable is happening here for the first decision, and the variable is happening here for the second decision. And as you can see, they're happening in different places. So if I chose an important sampling distribution which work for this, it would not work for this. So the distribution itself kind of seems to be the right distribution to choose seems to be kind of decision dependent. So whatever was a good sample for a particular decision will not be may not be a good sample for them. And this presents a major bottleneck in extending this nice flow to the optimization system. And that is what this topic will be. Okay, so this topic
you proceed iteratively.
Yeah. So the key is to find a particular sample which you can update very easily. That's exactly what we are going to do. So you cannot use a static sample because of this issue. So what you will do is you will do iteratively. So you slowly learn what the right sample is for the optimal decision. So that is what the algorithm, that is what this talk is going to be about. It's going to be about this adaptive importance sampling paradigm. And I'm going to show you an algorithm which is very scalable. So it just works almost in a problem agnostic manner. In addition to that, I'm also going to show you that unlike a lot of these algorithms which have been developed in the last couple of years, our algorithm requires you to do one scalar number. So just giving one number. So it's just a line search for a hyperparameter. You do this and you achieve the gold standard. So you get something called as logarithmic efficiency. So the number of samples which you require goes from 1 over beta to log of 1 over beta. So a huge reduction. Okay, and that's what this topic is going to do. Of course, the catch is that the distribution of X is known through its density. Okay, so I cannot evaluate this objective, but I do have access to samples and I know the density of X. Okay, why do I need the density of X? Well, I need to evaluate the likelihood. Okay, what happens in the data setting? Well, that is work in progress. I am happy to discuss it offline, but not first. So there are ways to use this objective and what the likelihood looks like to and like the asymptotic of the decision to kind of infer what the data algorithm is.
So let's say instead of knowing the entire the PDF, let's say I know that it's coming from the parametric family itself.
Yeah, very good. So you don't so in the data setting we don't even need a parametric family. It needs to be a very general one, semi-parametric family.
Okay.
So then you can actually get away with a very small bias. Because you don't know it exactly, so you'll incur a bias, but you should have the bias based. So and the family is very super general. So it includes all the, in fact I'll show you what it is. It includes all the latent distribution.
No, what he's saying is, in case it's coming from a parametric family,
Yeah.
you will do even better than what you would do in the data-driven semi-parametric setting.
Yeah, so if it's a large parameter estimate, then yes. But I mean, people don't really like making parametric assumptions in this world because you incur biases in the parametric assumption as well. So therefore,
It's a theoretical exercise.
no, they don't really like it. I mean, and okay, I mean, if you put some large version on it, there like estimating the parameter is hard, so it comes down to it's as hard as sort of.
No, I think it's probably worth exploring both the things.
Yeah.
Semi-parametric is
Yeah. But yeah, but once you have made a kind of a class of model assumptions, then you interface. Okay, so let me just do a brief literature review. So let me just do a brief literature review as to where the state of that is. Okay, and the kind of merging these various reduction techniques with optimization uncertainty goes way back to these two papers. It's like 30 years ago. They have done some important something for these multi-stage linear programs. So this is now long back. And then different people kind of have done different things. Exponential twisting is like really popular. So this paper and some follow-ups kind of try that. Again, this is very problem. This is very restrictive to one problem. So they consider a particular communication network with a particular class structure and a particular X, and it works out. So they do it for class metrics. The Markov and Monte Carlo for again two-stage linear programs. So again, requires two-stage linear programs with a particular distribution for X. And then we come to this work by these four ways, where they for the first time propose an adaptive scheme. So they propose a scheme which kind of tunes a certain importance and tunes a certain distribution parameter and iteratively learns the right importance. And that is also what we do. And what I do is I will briefly contrast their work from ours to the course of the talk. But basically, they propose a very general scheme, but don't give a particular a solution which sort of works for a broad number of cases. We do that. Okay, so this is the state of art. Typically, because of this issue with different decisions, you will sort of require an adaptive scheme to solve this problem.
You could take a, for each data, there's a right distribution that you have, right?
Yeah.
And you take a mixture across data of that distribution.
Yeah, but I mean, the mixture will be very large.
It'll be large, but it's good to have a benchmark and then say you'll produce.
So the benchmark is typically cross entropy for these things. I mean, that's also an iterative.
No, it's good to have that benchmark and say you're doing so much better than it.
Yeah.
You get some polynomial improvement.
Yeah. Yeah, I suppose because you need to put weights on all of them. So I mean,
yeah, throwing a sample all
exactly. Yeah.
But reasonable amount everywhere.
Yeah.
But then you don't have too many samples like you would have now.
Yeah.
But if it is an iterative scheme, so doesn't it make sense to do it in online fashion?
So this is kind of online. I'll show you. It's not like online. The data will come to you like one at a time. But we will update certain parameters of the underlying importance sampling distribution to arrive at that.
When you are actually sampling, you are sampling from the offline data that is available.
Yeah. You're sampling from the offline data, but the algorithm will update something.
Yeah, but they are assuming that the density is known. Now the simulation model is generating samples from it. Now you could have a more general framework where you learn the density as you go. Online. And that's an interesting problem.
Yeah, that will be very interesting because as you get more and more data, you get more and more accurate also.
Yeah. Because you're anyway doing it in iterative fashion, right?
Yeah.
That's right.
And anyway, so I'll show you like initially you sample very little so that you learn fast. Like you optimize fast. Okay. So this is the kind of scheme which we are going to follow. Okay, so you have a family of good importance sampling distributions P. So think of exponential family of distributions. They're parameterized by UK and theta. So U and theta are the arguments in this optimization. And we start with theta naught and U naught. And at every step you do the following. So these are oracles for now. I'll show you how to do these oracles. So at every step, you will get all importance sampling distribution by querying the oracle. Basically, you will feed these two numbers, it will give you all importance sampling distribution. Okay? And once you get this distribution, you will generate these importance scenarios from that distribution. So this is called a case step. Okay? Once you get these importance scenarios, you will construct something called the risk minimization problem. So RM, which is this objective, which is a simply the empirical, this is the leeway objective, empirical leeway objective, and you will minimize it. Now, what will happen is once you minimize this, you will get a decision UK data K. You will update the solution, you will feed it back here, and you will repeat. And you will repeat again some tolerance criteria. So you keep on repeating this over and over, some tolerance criteria is okay. The key here is this family P. If you choose the right family, you will get a good variance reduction. If you don't choose the right family, you will not get a good variance reduction. Okay. Why does this work? Well, it's kind of intuitive. As you proceed, as you draw more and more samples, because of log large number, these iterate are going to converge to the optimal solution. So I'm assuming the problem is convex, so the optimal solution. Okay. As they converge to the optimal solution, the important sampler which are coming up with is going to become better and better for that optimal solution, assuming certain continuity criteria. And so your variance reduction becomes more and more, your problem is more and more efficient. And so basically in turn, this causes the importance sampling distribution to be increasingly suited for the problem. It becomes better and better. And over time, it will just it will arrive at the right importance. Okay. Now there is some flexibility on how to choose these sample sizes and how much tolerance to solve this too, but I don't want to get into that here. So that's more in like numerical, like optimization literature. I don't want to get into this. Okay, but should you do this properly, this works right. And in fact, this paper by Key et al. They assume that it can solve the problem perfectly, so they don't really deal these numerical issues at all. Okay, now what are the known results in this? Well, they have a central limit theorem. The central limit theorem basically says that as you proceed, as t goes to infinity, if you choose the sample sizes properly, the solution you get here minus the true optimum has an error which is roughly equal to the variance of the important sample at the optimal solution. Okay. So whatever was the p at the optimal solution, whatever the variance of the objective under that p is the L2 error of this. Okay, so should you choose the p properly? Should you choose this family p properly, you will get a good variance. And that is what it is. So with the good choice of p is a very big if, and apart from very simple problems, they are not really able to demonstrate how you can
this is asymptotic, right?
This is asymptotic.
But then you're iteratively changing your theta.
Yeah.
So, but you're getting this optimal p for that particular theta. So
you're getting the so the optimal variance is actually the p for the optimal theta.
Yeah. Oh,
so that is what asymptotic will be.
Okay, not for the
That's
So eventually you're very good.
Eventually you're very good. Also, one thing you need continuity of these things in the right sense in the reversion. So the proof uses that, you have proof uses that. So but if your p was good for the theta star, then you will get the right variance. But that is where the problem lies, because apart from very simple examples, they are not able to demonstrate how they can choose p, and that is what we are going to show you. So basically, this is the implementation challenges. So like operationalizing this, there are two challenges. The first challenge is this step. Because I told you, like, to choose an importance sampling distribution, you need to do a large Bayesian analysis case by case. And what is a good family of importance sampling distribution is kind of governed by the large Bayesian analysis. So every time your problem changes, so every time the distribution rate changes or the loss changes, you have to go back and do a large Bayesian analysis and then come up with a P. And it's not even possible all the time to come up with this P just by doing a large Bayesian analysis. So that is not clear. So the first difficulty is identifying what a good family of importance sampling distribution. So what the P dot is. The second difficulty, even should you be able to do this. So by the way, there have been a lot of partial resolutions here. So Sandeep has a very nice paper on hazard rate twisting here. Glasser and all have a paper explaining this has been kind of there has been partial resolutions here for the last 20 years. Okay, so the second part is that even if you were to identify what the family of distributions is, you still need to set up an optimization confidence formula. And this problem is often non-convex or combinatorially very challenging. And to do this over and over again for every discipline, then your algorithm just takes forever to run. So it becomes computationally infinite. Okay, so there are two problems. One, what is a good family of distributions to choose? And even if you do choose the family of distributions, how do you actually solve the resulting optimization problem in a computationally feasible way? Because this is not a one-shot thing, you have to keep on repeating it over and over again. So solving the optimization problem multiple times becomes computationally feasible. Even in reasonably simple settings. Okay. Now, this whole thing is basically requires expert on large Bayesian and optimization. So it requires someone to actually set up a large Bayesian theorem, requires someone to set up an optimization problem, solve it. So these are very model dependent schemes. A slight change in the model is going to change the scheme completely. So we don't want this. We want a more kind of a model agnostic scheme. And what I should note down, or I should point out here, is that whenever you have a scheme which is kind of working for a particular model, we do not do as well as it, obviously because we are more general. But in these settings, I mean, very little is known. So our scheme is kind of the first which sort of integrates, which can solve a large number of real-world problems. Okay. And our contribution is basically twofold. The first one is to automate step one, so no more large-variation analysis case by case. I'll show you a very general large-variation result to sort of work on a very wide scale. And the second one, which I think is a little cooler from an optimization perspective, is that it actually reduces steps to solving a line search. So you just need to search for one single scalar parameter, nothing more than that. Okay, so we automate this and we sort of reduce the computational burden on steps to it. Okay, so in that way we are kind of resolving the difficulty in incorporating optimization in this. Again, then what I would like to point out is that whenever specific techniques work, they work far better than what our scheme does. So I'm not claiming anywhere that our scheme is in terms of variance the best. What I'm claiming rather that is far more general than exists. So broader applicability. Okay. Alright. So how do we do this? Well, our solution relies on this notion of structural similarity or self similarity. So word which we have coined, so self similarity. And well, these are kind of distributions for X which you will be using in broad mathematics. So if you're using portfolio varieties, you'll be using these. If you're doing machine learning, maybe these. If you're using risk management, maybe these. So these are the standard distributions. Alright. And what I'm going to do, remember the importance sampling distribution must place marks where the relevant place. Okay, just keep that in mind. What I'm going to do is I'm going to show you two pictures. And what our algorithm does kind of to be apparent from these pictures. In red, in each of these cases, is the conditional distribution of X given the loss exceeding the target level. Okay, so this is the level at which you want to evaluate this one. In blue is the conditional distribution of the loss given that it exceeds the level, which is like t by 10, so some fraction of t. And what you can see is at least in this setting, where I mean the decision data is static here. I'll show you what happens when you change it a bit, but the decision data is static here. So at least for this particular decision and this particular loss, it seems that across the board for all these distributions, the positions where the blue and the red points concentrate seem to be scaled versions of it. So if I take the blue points and I drag them out a suitable amount, I will reach the red points here. I will reach the red points here by dragging them out vertically across the axis, and I will reach the red point here by dragging them out across the entire profile.
So you're looking at nice distributions where the ray data looks a lot like non-ray data.
Yeah, but it will turn out that basically almost everything you will be concerned with. I mean, basically all the distributions which we usually look at. Yeah. So it's there are two very general assumptions which sort of allow this to happen. But yeah, you're looking at nice distribution where the relevance are sort of scaled.
You're keeping your dimension of X small, is that right?
I'm not very small. I mean, this works for about 15 to 20 dimensions. For 100, it will not work. I mean, it can't be scaled with beta. So you can't scale the dimension as the rarity goes. So that's kind of a bottleneck for us right now. Yeah, so it's a big dimension problem.
Because this property will be too large dimension.
Yeah, it is true. But the thing is that the concentration sort of becomes very localized, the volume is very small. So then when you try and do this stretching, it's going to go up.
But you can do something.
You can do something more intelligent. Yeah. Yeah, so there will be versions of this for large. Yeah. Okay. So basically, here's what would happen. So we want to minimize the objective. And I plotted the sample with a rarity of 10 power minus 2 and a rarity of 10 power minus 5 in 3. So 10 power minus 5 is where I want to evaluate this one. These samples occur 1,000 times more frequently in data than this. However, sample analysis will only use the red ones. So doesn't care about any information encoded by the blue samples. In fact, as you can at least see in these pictures, it is possible to leverage this information. So there is some structural information about the rarity given by samples which are far more frequently seen in data, so not that rare. And the cool part is that the blue samples are seen more frequently. So if you see one red sample, I'll need like 10 power 3 or 10 power 3 more computation efforts than to see one blue sample. So if I were to sort of somehow find a transformation which takes these samples, use that as the important sample, then I will get a sample reduction of 10%. Just because I'm seeing the blue sample that many times more frequently. Okay, and the rest of the talk is going to be about that and how to use that, how to incorporate that in this adaptive field.
Now, all these important sampling things work well when your likelihood ratio is well behaved. So you'll have that property in all of
Yeah, we have that. So the likelihood ratio can show in most cases bounded by 1. There is some usually these are monotone. These distributions are monotone. So if you are evaluating the likelihood here versus here, it's going to be kind of always less here. So all that works. So we have a variance here, like a full variance that will tell you like yeah. And that's it adaptive, like even after you do all this yeah. But the key part is kind of identifying from the transformation. So like what is this transformation that I mean because we want the problem, we want this to be kind of model agnostic. We need the same transformation to work for all these and for also for different kind of classes.
So you need the structure from the PDF, right?
Yeah.
That you know.
Yeah. Yeah, you need to, this is not going to work like absolutely everywhere. It's going to work when the PDF has certain very minimal structure.
I see.
I mean, it's not, it requires like just bare minimal, you need some, well, either the PDF has to be well behaved or its log has to be well behaved. Just under these two assumptions, just with that much. Okay. So basically, it's going to be okay. How do you identify the scaling? That's question number 1. And if I tell you what the scaling is, how do you put it into an adaptive wise? Because I claim that I only need to update a scalar parameter, so I need to show you how to do that. Okay. So let's identify the scaling first, and it's just this. All you do is you take a point, you multiply it by r power some magic exponent. Now this magic exponent is not unique. I'm showing you only one of the many possibilities. We have one more in our paper, in our full paper. But basically, what this is doing is this exponent needs to be able to replicate the blue samples in the red ones. Okay, you have these blue samples, it has to be replicate them in the red ones. And we have a technical large deviation result which kind of captures that replication. But I don't get into that here. All I want to know is the really simple transformation. It's almost regular continuous. It's almost regular differentiable. So that you can actually evaluate Jacobian and everything very easily. So you can actually just use this as the important thing. So what you do is you use T of x, T R of x as the importance center. R being how much is stretch out, how much is stretch out distance. If R is big, you stretch out very far away. R is small, you
so let's say your x is it's in a ball. Let's say infinity norm is 1.
Okay, so let's see what would happen to these samples. Okay, so let me write it down. Let me write down the transformation there. Let me show you. But maybe I have a picture here, and I'll show you like what happens afterwards in my terms. Okay, so remember because these events are also kind of rare, the x is going to have a somewhat large infinity. Okay, so let's see what happens. So here it's a 2-dimensional thing. Okay, so here the blue samples are both concentrated somewhere in the middle. So x1 and x2 are both reasonably large. So log x1 and log x2 are also reasonably the same. So when you hit these samples with t, they're both going to be stretched out by roughly the same. So once you apply t to these, you get the same. You kind of get the same kind of samples. So let's see what happens when samples concentrate in the corners on the axis. So here x2 is large, x1 is 0, which is kind of 0. Okay, which means that when you apply t to the first component of these, the first component of kappa is 0. So that component of it does not get scaled. So this stays where it is. The second component does get scaled because I mean this is roughly going to be equal to 1 or 1. So when you apply t to these, you kind of get this. So points on the axis, it keeps on the axis. Points in the interior, it keeps in the interior. And not only that, point anywhere in the space, it will keep all of the same large deviations continue. So we actually prove that. So we actually prove that this transformation keeps points anywhere in the space along the same large deviations continue. So they could be along the axis, could be in the middle, it doesn't matter. I mean, I'm not yet told you what are the arguments and this work, but under a very general set algorithm, this is going to sort of preserve where these contributions are. Okay. So what you do is you basically use this as the importance.
And what is rho here?
So rho is the regularity parameter which is computed. There's no only thing you need to know about the problem. But because it's the optimization problem, you know what loss you're optimizing, so you will know. You will know.
And R is also a parameter.
R is the hyperparameter. So remember I said that there's a scalar parameter you need to, then R. So that's really all you need to do.
But there's only one parameter. R to the 1 by rho is the parameter.
No, you know. So R is what you. So R you basically you will search for the best R level.
So I mean, you could have also called R to the power 1 by rho as well.
Yeah, we can. But the rho is like a problem parameter, so we sort of decided to keep it separate.
Since there is some scaling.
Again, because when you change the parameter, also like the loss is linear rho will be 1, then the loss is quadratic rho will be 2. So like we just wanted to have that symmetry, so we did. You can do it, you can do it. So that's why the R is the only thing you need to do. Okay, but basically it's not happening. The rho is kind of preserving the kappa is kind of preserving where the derivative is happening. So if it's happening here, it's stretching out numbers properly, happening here, stretching out numbers. And it happens when you still set up numbers properly. It will also set up numbers properly if the marginals of the x are different. So it will still work in that case. Okay. Now here are the assumptions under which we can make our things work, and these are by the way I call these assumptions light. Because in our paper, we have a far more general set of assumptions than these under which it was. But basically, what we say is that the loss is polynomial, well, almost polynomial. So here is the rho also. So rho is the degree of the polynomial of the loss. Typically, it's going to be 1, and you don't often 1 or 2, and you don't often optimize for things which are more than 1. So this is the assumption of the loss. More interestingly, is the assumption on the distribution of x. And this is what I feel is very cool because whether your x is light-tailed or heavy-tailed, so long as it's PDF or it's log PDF is kind of polynomial in the same way as before, this is going to work. And here I don't think we need to know what degree of 1. It can be. It could be degree 1, 2, 3, I don't care. And I'm showing you the other thing that all of the components can be the same degree, even that is not necessary. It can be a polynomial of different orders. So it can be like you can have crossovers. So this is like a super general assumption, which is satisfied by, for example, homogeneous kind of losses. So the portfolio optimization problem. There's something called a two-stage problem. So this is very common in like when you're managing capacity of large plants. So it works there. It works for linear programs. It also works for stuff which is driven by neural networks and neural decision component. It works there. So we have a lot of examples in the paper. I can share it with you if you want. Okay. So that's for the last. For the x, the first assumption is like this. So when the log of the PDF is exponential, so is polynomial. So think of quadrant. You've got e power minus x minus mu over 2. So basically, we are looking at this. So the mu gets filtered out, and so the phi side becomes x transpose sigma minus x over 2. Okay, so stuff like this. The second one is more like multivariate t, where it looks like something like this. I don't remember the constant, but
So if you use these as defining properties of distribution,
yeah.
They say let's select all the distribution satisfy this property or second parameter. Can you say something about those classes?
I think
you have this first property at the top, and you're calling that light tail. And there's a second property. These are two separate classes. But if I just look at those classes of distribution, can I say something more about them? Besides,
I mean, property wise. So these are actually extreme value distribution. We're just calling them light tail and heavy tail. So these are extreme value distribution where the extreme value parameter is positive. These are extreme value distribution where the e power the distribution that has a.
so it's well known.
It's well known, yeah. I mean, it's not very known. It's not like well known. It's a very recent sort of a thing. So these are classified log values. So like to take the log of these become like e power these become okay. So this is like the log normal version of Bible, and these are the standard variables. So multivariate variables. Multivariate variables. So multivariate E, multivariate Pareto, and so on. So these distinctions are been studied recently. And in fact, I mean, in our paper, we don't make assumption A. We make assumption on the popular version. So what you do is you standardize the margin of the wave to be exponential, x to be exponential. We make assumption on that. So we assume that follows a very simple large principle, and then we derive ourselves. So that's why these are assumptions light. I mean, because I just wanted to show something specific. So we do something fundamental than this. Okay, so light tails are all these. I mean, these are basically a huge family of distributions. What I really found cool is when you take any of these and you form a mixture, and it still works. So even like for 3 or 4 slice like large mixture, you have tested it does work. You take any heavy tail and a light tail to form that mixture, it will still work because it will satisfy this property. And you can do lots of things. So this is a very, very general class of distribution for which one can use this concept. Okay. Now what I want to do for a little bit of time is I want to show you the mechanics of this. So I want to get a little bit into the math. This is going to be the most kind of mathy side of my entire talk. So just about 5-10 minutes. So basically, you want to find what the probability of this event looks like as t becomes large. Okay, and that is going to govern where this mass is. And what we show is that under those two very general assumptions, we show that the probability looks something like this. So this is a validation result which we derived in the previous paper. So the cross points are basically something called as rate points, and the rate points are where the mass concentrates as the t becomes more and more. So as the event becomes greater than 0. So the rate point is basically just the argument of some optimization problem. What I want you to focus on is one here. Okay. So argument of some optimization problem index by 1. Now this is for t, which is the target level. Let's look at what happens when you replace the target level by something which is a fraction. So like 1 volt is the target level. Well, this was the same optimization problem, but not with 1, but with 1 volt. Okay. And what happens is because of the homogeneity, asymptotic homogeneity assumption on the entire side, if these crosses are done, you can take these points to these points under all assumptions which I showed you previously. Those transformations will lead to concentration preserving, and those transformations will actually be good importance. And what I showed you was one example, paper has one more, but I mean that's essentially it. Okay, so basically any transformation will take these points to these points, will also take these points to these, and that's what we find. And also for the others. So the mechanics are really given by these variations here and here. And the reason why this works for all the general settings I told you is because this variation doesn't work for all the general settings I like under all the assumptions I told you. Okay, so this is not case by case, this is for like this whole pattern. Okay, so that identifies the transformation T, and we have a proposition here which is like an informal version, there's a formal version in the paper. So theoretically, optimal sample, so points here, and if you take these guys and you transform them, they kind of concentrate mass at similar points. So basically, the rate point here and rate points to this. Okay, the transform rate points and these rate points to this. That's what the theory is. Okay, so fine. Now that's about how to identify this thing. Now we still need to see how to incorporate this into the adaptive scheme, and for that, well, the solution is very simple. All you need to do is at every step you find the best state. So this is done by calling like this the line search for over like this, finding the state which minimizes the objective variance. So you get the best state. Now I told you need to generate important scenarios. So you don't generate important scenario anymore. Just sample from S and state. So the important scenario will become this transformation. So you don't really need a separate mechanism to generate the alternate samples. You already have that mechanism. So you get the base state, you generate alternate scenarios, you solve the same display management problem again, you update and you keep moving over and over. So just to reconcile with the previous notation, here P is the distribution of T of TRQX. Okay. So what's happening here is at every stage instead of getting this huge object, this huge probability distribution is getting just one scalar. So therefore, the search for this importance and redistribution gets reduced to this place. The line set being on the empirical variance of the object. And you keep repeating this over and over again until a particular tolerance is met, and we have this, and then this works. Now, what I want to show you is actually how this works. I just want to get into the actual mechanics of this. So what I've done is actually two-dimensional process, very simple one. And in blue are the transform samples, so TRA of X, so TR1 of X, TR1 of X, TR2 of X. These are the conditional samples for that particular distribution. So remember, this is the identity, so every stage it sort of runs this, updates the distribution and repeats. So these samples it's mimicking, the transformation mimicking. Now, after one step, the R is going to get updated and the theta is going to get updated. The R gets updated here, the theta gets updated here. After one step, the decision is changed, so the theta is changed, but still the important samples and the transform samples are kind of matching, and they match again. And as you can see, after two steps, the matching stops, because this decision and the decision is okay. So it counts out. So it actually takes a small number of steps here, just by doing this sequence. So this is a small problem, so 2 dimensions, or in a larger number of dimensions, it can take fewer photos, but it's still a problem. So computationally, this is like really simple. Okay. And I think in this case, I've not even done a line search, I've actually optimized over the R. Like I've used the one-dimensional optimization in Python to find the best R, so I mean, even for that one. But the key takeaway here was like, irrespective of what the decision is, the important sample is tracking the optimal distribution just very nicely. And this is not just with this particular example, I changed the distribution it still goes. Okay, so in this case, I mean, initially it was here. Finally, I mean, this seems to be concentrating on the axis, but both the transform samples and the truth are concentrating on the axis. So this seems to be irrespective of what this seems to work irrespective of what Robin is choosing.
So what is the rate of convergence in terms of number of iterations?
Oh, that we don't know. I mean, because it's asymptotic result, it's the center limit theorem. So that
in terms of the iteration, not the number of sample points.
Oh, in iteration, okay. So there's a way to choose the. So okay, so the center limit theorem is like square root of k times theta k minus theta sum goes to normal something.
So square 1 over
yeah, 1 over k iteration, but the normal sample you need iteration is kind of increasing k. Right. So one can also write it in terms of that, but generally, it is retrospective things are written in terms of in K. And then you just choose the number of samples in each step. So there's one more property which I not mentioned is how accurate is solve this optimization problem. So that's a computation step. So even that one can optimize.
X's you're generating again and again, or just
no, it's once.
So once you generate these X's, you have your theta that tells you where to move your
way
to push your points. And then you again subsolve then you get a new way to push your points.
So that's what's very cool because you don't need, I mean, suppose you sample the 10,000 X's and then every sampling is simple. You don't need to resample, you can use the same X over and over. You just need to take them out in.
Yeah, but you're assuming that you know the density of these things. You can always resample, right?
Yeah, but I mean, you can resample it.
I guess in the data driven setting.
In the data driven setting, we don't have transformation, we have something which means a transformation. And then there is certain errors.
Right. That's probably more interesting, man.
Yeah, it's far more interesting. I mean,
data is expensive, it's already there. And
yeah, but it's also not harder because you can't really have this. I mean, you have to deal with the bias, which comes out of making some approximations which you need to do.
Yeah, no, this community kind of worries about bias, but in practice, bias is okay.
Yeah. I mean, everything actually we found in database is doing very well. There's no reason to believe like there's a bias over the work in practice. Okay, so fine. So how does it address like the conditional difficulty? One is that you only access samples of X, so you don't need like a whole family of distribution which you need to sample from. You just need one. If you have X, you can implement this. And two, because the R type is a scalar, just do a line search. Choose your favorite objective, do a line search. If that objective function is good, say for example the object like the variance of the optimization problems, then this works. Okay, it's just the same. And in fact, I mean, this code just is like, it's just a few lines of code. It's not in big. So just writing three functions, then that's it. The bottleneck here is obviously dimensionality because it doesn't work for a high number of dimensions. For the reason that the volumes become like really, really tiny, so you can't stretch out things properly. And also sometimes does not work if I mean your losses are not like super homogeneous. I mean, if you choose a loss which becomes homogeneous very, very far from the origin, then this will work. So that apart,
dimensions you can do something like dimension PCA or dimension reduction techniques.
Yeah, so that we can try. That is certainly something we can try. But I mean, so the application which we had in mind was power networks, where the dimension is not an issue because you only have like 3 or 4 renewable sources of energy which we sort of want to render. So this particular application doesn't have high dimensionality, but I mean that's something which anyways you want to sort of think. The other one is like actually having a dynamic setting, like you're saying, where you have samples of X coming from also dynamically, you can't just do them, sample them first. Yeah. So okay. So let me show you the only theorem which I'm actually going to state because of the tutorial. So the theorem is the following. So if you want to, so for a particular algorithm, let's assume that n, a, and g is the number of samples required by that algorithm to estimate the CY to within an error epsilon, so relative error epsilon. Then for any delta greater than 0, you have something like this. So the amount of samples you save by using importance sampling is roughly beta power minus 1+. Now, if you don't like this particular form, let me show you in more precise. So you get something like this. So if you don't like this, if the sample algorithm is taking like 1 over beta times the constant number of samples, we take minus log beta power from k number of samples. We don't really need to know what this k is, but in practice we have observed that it's quite small because I'll show you get a significant drop in number of samples. Okay, so here's the full algorithm, right? Just a basic of it. So you solve the CY problem, update the parameter, solve it up to tolerance, repeat it. Okay, this is the algorithm, same one which I showed you. And what I'm going to show you is I'm going to actually implement this on a 15-dimensional portfolio optimization. Okay, 15 is not like a very small number of dimensions. It's not very large, so it's reasonable. X is here drawn from a Gaussian copula, so the dependencies through a Gaussian copula. The catch is that the marginals of X are not identical. So they're minor marginals but with different densities. Okay, so the marginals of X are not identical, but the dependencies through a Gaussian copula with some correlation matrix which we estimate from data. So it's not like a very straightforward. And I have two graphs for you. The first one is the regret. So here what we do is we find the optimal decision, we evaluate the CY and that optimal decision, take the difference between that and the two optimum and find the relative. And we do this every beta small. This is for 2000 samples, this here we vary in the first. So here number of samples is fixed, here that is fixed. And what you can observe is that as beta becomes smaller, the regret for the sample average becomes big, obviously, because the solution is bad. The regret for our important sampling, the red solid line, stays small. So great, that's doing well. But what is interesting is the pink one. So the pink one is our important sampling, but without tuning. So you don't tune, just choose one particular R and just stop. Okay. And what you can see, initially it's doing okay. But as the correlation becomes better and better, if you don't tune the R, although maybe not tuning the R is fine, in practice it's obviously not. In theory, it does not matter if you don't tune the R, it will give a similar asymptoticality, in practice obviously will be bad. Okay, so this is an extra type of tuning actually this. So it's not just something which is it's like a theory construct. Okay, now on the right is a graph where I kind of have plotted the number of samples required to get 1% tuning. Okay, and as you can see, there's a huge difference in this. So this is performing well in sort of both these sort of areas. Fine. So that is what I have to say about CY minimization. Now in the last 5 minutes, I want to spend a little bit of time on the safety constraints. Now this is numerical because we only started this a couple of months ago, but we have some promising results, so I thought I should. Remember this problem was like maximizing utility such as CY kind of is bounded by some S, so some safety constraint is met. And what you do here as well is replace this by its important sample average, and you will repeat the same algorithm with an extra step here that you check for some optimality gap and then you stop when the gap is smaller. And what I want to show you is these two pictures. Okay, so the first picture is the actual value of the CY, actual value of this for the solution which you have come up with, where you are writing n equal to 1000 samples. Okay, alpha is the regular, so beta is 1000. You can see that the sample average is the blue line is grossly overestimating, is grossly giving a much larger risk than the tolerance with 10. You can see also that the degree of repeatability for our thing becomes smaller and smaller. In fact, it's actually feasible after just 5 minutes. For this one, this is the optimality gap. Okay, so this is so this is the optimality gap. This is the same thing how far the theta and y important sample is from the true optimum. So you can see that the optimality gap for the Monte Carlo is like a sample average like 25%, for I think it becomes like 3%. So even in this setting, at least numerically it seems to be very good. The key part is that the important sampling is both reducing the extent of infeasibility, so the solution is actually feasible here, and also reducing the. So this kind of prompts further explanation. Okay, so that's all I have. I kind of spoke about how one uses huge body of literature and dynamic simulation, combines it with optimization under uncertainty, and sort of comes up with nice important sampling schemes. So data driven setting, I'm very happy to talk about, but that's it. These are some future directions. This by the way is really, really cool because it's using some very cutting edge tools of statistics. So it's statistical devising, if you've heard of it. So it's using that. There are some other works which we are doing. Some of these are available on my webpage, and if you want to email me, please do. So thank you for coming.
Yes, so I forgot to add that how we did that you were IIM Bangalore.
Yeah.
And if you learn how to teach and you learn how to teach every year. So if you know Anand from 2 years ago, you know he's learned a lot. Very thanks.
Huh?